Well, first of all, I want to thank the organizer, in particular Roland Pothas and Takemasa Miyoshi, for inviting me to such an important event on DA. So, well, yesterday we saw very impressive results on the application of particle filters for cyclones. And today we are going to come to the same topic, but from a much more mathematical perspective. I hope still that is appealing to everyone. Well, so I will show some recent results we have had in the University of Potsdam. This investigation has been conducted under the lead of Sebastian Reich and with the collaboration of Maria Reinhardt. And well, I want to acknowledge also the support we have received from the Collaborative Research Center, Scaling Cascades in Complex Systems. Okay, well, so within a filtering context, we all know the traditional approaches. On the one hand, Kalman filter, which offers a completely parametric approach. Everything is Gaussian. And with that, we get a very robust and moderately affordable approach, which nonetheless is biased if we happen to play with non-Gaussian PDFs. On the other hand, traditional particle filters have no assumption on the shape of the PDFs, and because of that, are able to handle non-Gaussianity appropriately. However, it's well known that they suffer from this course of dimensionality, meaning that the number of particles needed to work well grows exponentially with the number of dimensions. And because of that, they are very prone to collapse in high-dimensional systems. Let's say this was the state of affairs kind of 10 years ago. But recently, there have been several developments, in particular, localized particle filters. So that's an idea that now became quite kind of widely used. On the other hand, there have been already some tries to mix Kalman filter and particle filters, so that in order to find a trade-off between the accuracy of particle filters and the affordability of Kalman filters. On the other hand, there are also some ideas of using optimal transportation theory on that, and I will go in detail on that approach. And also, there are some very interesting and theoretical insights right now coming from Andrew Stewart's group, speaking about the intrinsic dimension, which is something that is kind of shedding light on why particle filters can work at all. Okay, during this talk, I will use the three first ideas that we utilize to create a hybrid between particle filter and Kalman filter that has some special properties we think can be very promising. And so in particular, we want to contribute to this dream, to make this dream of having non-Gaussian data assimilation methods running operationally. So we think that this can give some insight. Okay, so first of all, I'm going to introduce the framework of linear ensemble transform filters. Afterwards, I will speak about the particular hybrid approach we use. Then I will show how it works for a single DA step, how it works also for when we have a dynamical model, without special variations, and afterwards how it works when the model is spatially extended. And finally, I will give some conclusions and prospects of our work. Okay, so linear ensemble transform filters is a framework introduced by RIKEN and Kotter, where given a forecast and analysis ensembles, the update is going to be expressed as a general linear transformation. It's important to notice here that this transformation acts upon the whole ensemble. This is not just the anomalies, like the traditional Ensemble Transform Kalman filters, but so these are the members, they are the particles. So this transformation should satisfy some constraints. In particular, along the first dimension, they should sum up to 1, meaning that we have affine combinations of the forecast. And the other direction can also add up to, to find some weights multiplied by the size of the ensemble. These weights do not need to be important weights. In particular, they can be negative. So in that case, they cannot be interpreted as important weights. And so this can be a very interesting diagnostic, as we'll see right now. For example, we can bring very easily the ensemble square root filter to the shape of a linear ensemble transform filter. We just add up the update of the mean and the anomalies to get this expression, where the entries are given by 3 terms. These are the entries of the typical square root matrix. Here we have some weights, which are given by this formula. These weights are not, can be negative, as we will see. So they cannot, in the case of Kalman filter, they cannot be interpreted as important weights, although they add up to 1. So that's the Kalman filter we are going to use in our hybrid. Now, regarding the particle filter, we will use the Ensemble Transform Particle Filter introduced by RIKEN, which consider the update step as a joint probability between the forecast and the analysis. This joint probability should have as marginals the weights of the forecast and the analysis. And this can be expressed very easily like this. So the analysis mean is going to, as every particle field, is going to be given by a weighted average of the forecast, where the weights are given by the likelihood function here. So they are proportional to the likelihood function, and they are furthermore normalized. And this joint probability can be expressed in this way, where these entries are the entries of a matrix that satisfies several constraints. In particular, again, we have this constraint over the sum along the first dimension. And on the second direction, we have, again, weights. But in this case, they are proper important weights. And additionally, these entries should be non-negative, which means that these combinations are not only affine, but convex, which is much more restrained. And so, until this point, we have what is called a coupling. But couplings are not unique. So in order to make this problem unique, we are going to enforce this constraint, which is to minimize this cost function, which has here the entries of the transformation, and here the square of the distance between particles. And so the particular matrix for which this cost function is minimized is going to be called the transportation plan. And that's going to be exactly the transform. This problem, so posed, constitutes an optimal transportation problem, where the idea is to morph these these weights, the forecast weights, into these ones, which are the homogeneous weights of the analysis, in the sweetest way possible. So this cost function I just introduced penalizes transport between very distant particles, so that this flattening of this surface into this one happens in the cheapest way. So this optimal. So this is so the meaning of this function is called the optimal transportation cost, but because of the analogy I just made, it's also known as the Earth mover distance. And as opposed to other distances in probability spaces, it takes account of the shape of the PDFs. And the corresponding mapping, the corresponding transportation plan is called the optimal coupling, which has the very interesting property of maximizing the correlation between forecast and analysis. Furthermore, it's deterministic, and because of that, the fields we get are going to have the same regularity as the forecast weights, as the forecast states. Sorry. Well, this setting is consistent with base formula as shown by Reich in 2013, and furthermore, because of this maximization of the correlation, the convergence is faster compared to sequential important resampling particle filters. Of course, at the cost of solving a more expensive problem, that is the optimal transportation problem. This optimal transportation problem can be solved in different ways. It can be solved exactly, when in that case, we have to face a computational complexity of n to the third times logarithm of m, which is more expensive than Kalman filter, which are just n to the 3. And in particular, there are some very efficient algorithms right now, mostly based on graph theory. And in particular, this one, FastCMD, which is the one we use when we want to solve it exactly, works very well. That can be a bit expensive. Because of that, several authors have attempted to find approximations with lower computational complexity, as is the case of Couturi, who proposed to regularize the cost function by adding this additional term that has the shape of an entropy. And by doing that, it's possible to use an iterative algorithm that delivers the solution and has a computational complexity n to the 2 times a constant that depends on alpha. It's important to notice that this constant grows with alpha. So for very high alphas, which is kind of near to the exact solution, this gets very high. Additionally, we can go for even cruder approximation, that is the 1D approximation. We can update each variable independently. We can solve an optimal transportation problem for each variable independently. And by doing that, the problem reduces to a shuffling, to a reordering algorithm that is much cheaper. It's just m times logarithm of m, which is very nice. And additionally, the particle distance I already spoke about is not needed. So that's something very good. But of course, we are destroying the multivariate structure. But there are ways to tackle that, as we will show later. OK. So here we can see how, for example, given these prior particles and an observation in between, how the Ensemble Transform Particle Filter works. So this particle, this one, is going to have a high weight, and because of that, it's going to have more offsprings than the other particles. This one, for example, will have no offspring. And the members go near to the observation, which is good. Kalman filter will do something similar. They also go near to the observation, and the weights are have this particular shape. And interestingly, the transformation has already some negative terms and a very strong diagonal component. And now, if we, instead of solving the full transformation, optimal transformation problem, solve the entropic regularized one, we get now similar results here, typically a smaller variance of the ensemble, and the transformation is going to have many more non-null entries, but it still resembles the original one. So it's like a blurred version of this one. So that's what we get using this synchronous approximation. OK, that's the case when the observation is very nicely located in the middle of the ensemble for a one-dimensional space. Now what happens if the observation is outside of the ensemble? Then we are in problems for the particle filter, for every particle filter, not only this one, because the observation is not into the convex hull, meaning the possible states you can get by convex combinations. If that's the case, the particles are going to just be drawn towards the observation, but they cannot go farther than this. So they just jump into this wall, and then you have a strong degeneracy, while the Kalman filter is able to pull them very nicely towards the observation, at the cost of having very negative weights and very negative entries. So this is both good and bad, because, of course, if we are playing with positive definite quantities like rain, that would be very bad. We can produce negative rain, for example. But in the case of having a model bias, in which case we will be always like this, the observation will be outside of the convex hull, the Kalman filter will give us a lot of robustness. It's able to pull them there, no matter the observation is just outside of the ensemble. So that's something very interesting about the Kalman filter, about a very interesting insight that we get from the weights of the Kalman filter about the robustness of it. OK, now let's go into the hybrid. So I already show how this linear ensemble transformation can be used, and these weights can be used to understand what is going on with the Kalman filter and particle filter. Now let's see how can we set up a hybrid. So for that, we use the idea introduced by Freire and Kunsch, that is to split the likelihood. So here we have the likelihood. We are going to split it in two terms, like this, by introducing an addition, a bridging parameter, we call it alpha. So it's the same function, just split it. And now we are going, so we can put this alpha actually below the R, and here the 1 minus alpha below the R. And we can see here that now we are going to have two updates, but with higher observational errors, which is good because now we are not introducing additional information, as it should be. And we are going to update this part with a particle filter, with our ETPF, and this one with a Kalman filter, with a Ensemble square root filter. And here, if we set alpha equals 0, we have a pure particle filter, which is the baseline, which we know is very robust. So if the situation is bad, we are going to go in that direction so that the filter doesn't collapse. And if for alpha equal 1, we have a pure particle filter. And in between, we have a mixture of both. OK. In order to understand to get some intuition how this hybrid works, we have played with different models. So we have made many experience with single DA steps, with Lorentz 63, Lorentz 96. We have also coupled it with a wave equation to see how the balance is affected. Shallower equations and modified shallower equations. So these are our explorations so far. Today I'm going to focus on these three, the simplest one, so that I can go into the details of the different mathematical aspects. I want to mention also that we are currently collaborating with the German Weather Service to implement this filter for the service. So hopefully very soon we will be able to play with Cosmo and Icon. OK, so let's go for the one-dimensional DA step. So here we can see how it works. I mean, how this bridging parameter is going to affect the weights and the transformation. So for a bridging parameter equal 1, we have a pure particle filter. And here we can see that some of the particles have very high weight, while others have no weight at all. On the other hand, the Kalman filter has completely equal weights, and correspondingly, the transformation is just diagonal. Doesn't do anything. It's completely disabled. While the transformation here is producing many offspring for this one and for this one, so proportional to the weight. Now, if we reduce the bridging parameter, we can homogenize these weights. As you can see here, become increasingly homogeneous, more homogeneous. The transformation starts getting more and more diagonal. The diagonal terms become stronger. And the Kalman filter starts becoming, so the weights, some of them become very negative, and the entries also. And in the limit of bridging parameter equals 0, we have, again, a completely inactive particle filter with equal weights and identity transform. And all the job is done by the Kalman filter. So that's how this bridging parameter is allowing us to homogenize the weights of the particle filter so that we avoid collapse. We have tested that for some analytical PDFs. So we have, for example, here strongly bimodal prior and a Gaussian posterior likelihood, and this would be the posterior. And we have made these estimates using the hybrid. And what we have found is that for smallest ensemble sizes, it's always better to stick to the Kalman filter. And we get, in order to get the smaller errors. But at some point, it starts being profitable to give some of the observation information to the particle filter. And as we increase more the ensemble size, we can go further and further, and eventually we just use the particle filter alone in order to get the best results. So this is how it works for a very simple case, just 1D. Now, if we want to to play with a dynamical system, of course, we have the problem of not being able to sample appropriately the state space. So we have to introduce some mechanism to fight this under dispersion. And in our case, instead of using inflation, that is the typical method, we are going to use the so-called particle rejuvenation, which, given an analysis, adds random combinations of the forecast anomalies. Here, this parameter beta is called the rejuvenation parameter. This modulating how strong is this noise here, this Gaussian random variable, which is Gaussian and has 0 mean and variance 1, so that the mean of the ensemble is not affected. It's very important to notice here that these random numbers depend only on the number of the particle, and because of that, they do not destroy the regularity of the fields. So the random numbers are different for different pairs of particles, but it's not. It doesn't depend on space. Good. So by doing this, we can increase the spread by preserving the mean, and we can ameliorate strongly the degeneracy of the particles, which is very important, of course, without destroying the regularity. Okay, now, so let's play with the Lorentz 1963 model, the most traditional model to play with, and we observe it rather sparsely. So we let this nonlinear dynamics evolve so that we have a strongly non-Gaussian case, and observational error variance equal 8, rather high. These are the results we get for different ensemble sizes, and this is the root mean square error. So for ensemble size equal 10, we can see, for example, that alpha 0, that is this line, is already outperformed by this one, that is alpha equals 0.17. So in this case, already using a bit the particle filter is giving an edge. But we cannot go much farther. If we increase alpha here, we are going the scale is going to be reduced. But if we use higher ensemble sizes, we can go further. For example, here we can go to 0.33. Here we can go to 0.50. So as we increase ensemble size, we can go to higher alphas, and we can reduce the error further. And these, very similar results can be seen if we look, for example, at the cumulative range probability score of the forecast. Okay. One important aspect of this hybrid is that we can either update first with the particle filter or with the Kalman filter. That's completely okay because both have transform structure. We can just exchange it, which is not the case of other hybrids. So that's something good about this hybrid. We can just select either particle filter first or Kalman filter first. There's no limitation on that. And the question is, which direction, which ordering works better? Here we can see how it works for Lorentz 63 again. So this is the plot we just saw. And this would be the same plot, but now updating first with the Kalman filter. And as we can see, this improvement we found here for this particular sample size is much smaller. So it happens to be much better to use the particle filter first in the case of Lorentz 63. So later I will discuss why. Okay, now another important aspect is what is the relevance of solving the transfer problem either exactly or approximately. And that we can see here. So this is the exact solution, the same plot as before. Now, and this one using the regularized version of the optimal transportation problem. And as we can see, the scale is very comparable. So in this case, it's very nice. We can use this synchro approximation, and the scale is still there. We can still outperform Kalman filter. Now, if you go further and use this 1D approximation, which is very crude, we can still, not for ensemble size 10, but for 15 and this one, we can still outperform Kalman filter with this 1D algorithm, which is really, really cheap. So although it's so crude, it's still keeping this skill of the hybrid. Okay, so that was regarding dynamical systems without spatial extension. Now, if we want to play with extended systems, as is the case of meteorological models, we have to take care of, we have to use localization. So we use the very traditional approach of the R localization, where this function is a tempering function. So we use RIKEN as is customary, and and we applied to the Kalman filters. It's already widely done, so we can apply it very easily to Kalman filters, and also to the important weights. These important weights depend directly on these entries. So if we localize the entry, we also localize the important weights. But there's an additional component that is the distance, the observation distance, and that one we localize by doing this. So instead of taking into account the global distance, we are going to take into account a local distance that we can find by doing this integral putting here this row as a kernel. Okay, and then we tested with the Lorentz 96 model that we all know. And again, this time I'm not going to change the rejuvenation, it's just fixed. Also, long interval periods. And so a customary setting, but with long observational periods so that we let the dynamics evolve. And here we can see the results. So we have different ensemble sizes here for different bridging parameters. So for example, for ensemble size 20, bridging parameter equals 0.2 gives us, again, an advantage over the pure Kalman filter that would be here. And if we go further, if we increase the sample size, we can increase this reduction of error. An important aspect of spatially extended systems is that it can be that the conditions for the particle filter are good in some areas, but in others not. So then it would be important to apply some kind of adaptivity so that we can split the likelihood in different ways in different areas of the domain. And that we have done so far using this quantity, that is the normalized effective sample size that is giving us a measure of the diversity of the ensemble. It has this shape. So for alpha equals 0, we will always have a 1 as theta, as normalized effective sample size. And as we increase alpha, this quantity is going to go down. And the way it goes down depends on the observational error. So what we are going to do is to say, okay, we want to set an alpha so that the effective sample size never goes below this particular threshold, so that the particle filter will always work robustly. Okay, and that we do what we did with the Kalman filter, with the Lorentz 96, and these are the results. So if we compare it with the previous ones, we can reduce the error considerably, especially for higher ensemble sizes. Okay, so finally, we also tested the difference in between the ordering, and it having not to be that important in this case. And we think that the fact that Lorentz 96 is not that nonlinear makes it like that. So we can either use particle filter or Kalman filter at the beginning, and the results are very similar, although we can still outperform Kalman filter. Okay, so to sum up, we have found that this proposed hybrid scheme allows consistent localization of both filters because of this common transfer structure. Also, the regularity of the fields is preserved. We don't destroy it, which is something very important, given that there are the random numbers involved do not depend on space. Additionally, we saw that we can outperform particle filter and Kalman filter if we set this alpha parameter well. We also saw that we can approximate this optimal transportation problem, and still we have a skill, and in particular we can do it. We can use this very crude approximation, and still we get a skill, which is very good because this is very cheap. Yeah, the update ordering happened to be important, but this seems to be model dependent. So this is something we are studying further. And yeah, the adaptive splitting of the likelihood seems to be very beneficial for extended systems. Currently, we are working on the one hand, implementing these algorithms for the German Weather Service. So we have had some problems regarding the observational particle distance, the particle distance, because it's not, the localized version is not really readily available. So that's something that has hampered the implementation, but we hope to be able to run the system quickly. We also have tested some new ideas on adding new constraints to the particle filter. We can, for example, following the ideas of Lee and Bickel, we can make the ensemble transform filter more consistent with the second moment, so an exact second moment, which we think, it's on the review, we saw that the conversion is faster. And yeah, so that's something very interesting. And yeah, and finally, we also are trying to apply to complement this 1D approach, which is so cheap, by introducing the copula. We hope to be able to reinforce the multivariate structure by doing that. Thank you very much.